Hi, I'm Tamara Broderick. Thanks for listening to this talk. So today I'm going to be talking about how we can make a really small tweak to the awesome dominant method in variational inference right now. And we get out a method that's not only more automatic, but also faster and more accurate. I want to highlight the two awesome co-first authors of the paper that I'm going to be talking about today. I was very lucky to have Ryan Giordano as a PhD student and a postdoc, and now he's a professor at the University of California, Berkeley. And we were both very lucky to work with the amazing Martin Ingram, who's now doing awesome things in industry. Okay, so at a high level, today we're talking about black box Bayesian inference. Amazingly, it's already been used in a ton of super awesome applications in science and social science. Just as a small taste, this includes the US election predictions from The Economist in both 2020 and 2024. It includes many of the most influential COVID-19 papers, and it includes a lot of fundamental science related to, for instance, the first observation of gravitational waves and analysis of that data. Why is black box Bayesian inference so widely used? Well, it has this amazing promise that the user just has to specify their model, that is to say, their prior and their likelihood. They give us their data, and that's it. They don't have to worry about tedious derivations of an algorithm to approximate their Bayesian posterior. They just can focus on their science and social science. Now, a really, really popular method of doing black box Bayesian inference is using Markov chain Monte Carlo. But the problem with Markov chain Monte Carlo is that often practitioners find that it's too slow to run in practice. They'd like something that's faster. And there's a hope that variational methods might be able to provide this. So in particular, probably the dominant variational method right now is automatic differentiation variational inference, or ADVI. And ADVI does exactly this thing that we wanted. It does not require manual derivations of an algorithm for approximate posterior inference. But remember, the promise here of black box inference was that the only thing the user needed to do was to specify their model and data. And so there might still be some gaps to getting to that goal. In particular, ADVI does require tuning of some algorithmic parameters. You can get perhaps some bad performance sometimes if you're not doing that tuning. And it lacks clear convergence criteria. We don't really know when we're done right now. Moreover, ADVI inherits from other types of variational inference that the uncertainty estimates it gives can often be quite bad in practice, like decision-changingly bad relative to exact posterior inference. And so, we don't just care about speed and automation. We want our methods to be fast and easy to use so long as they're sufficiently accurate. And so what we suggest in the work I'm talking about today is that we just make a very slight tweak building on the awesome work of ADVI. In particular, where ADVI approximates the steps of an optimization algorithm, we say, hey, let's instead approximate the optimization objective and then run a standard out-of-the-box optimizer. This is such a great idea that two groups had this idea at the same time. So I encourage you to check out this really awesome concurrent work from Baroni et al. At the end of the talk, I'll give the information for both our paper and the Baroni et al. Paper so you can check them out. In our paper, we show via theory and empirics that in common Bayesian inference problems that people encounter all the time, the alternative that I just gave a little hint at our proposal, and I'll go into more detail shortly, that alternative is faster, it's more accurate, and it's even more black box than ADVI. Okay, so for the rest of the talk, I'm going to spend a little time setting up what is ADVI, what is this new proposed method doing. I'll talk about some high-level pros and cons of these methods, and then we'll go into a lot of experiments. Okay, so let's do a little setup. So we're going to call our data Y in this talk. We're going to call our unknown parameters theta. Those are the unknowns, the things that we want to learn about. And in particular, we want to get a posterior over them. So we'll call our posterior P of theta given Y. It's some distribution in a space of distributions. And the problem for us is that we can't report the things that we want from the exact posterior. So for instance, we're often interested in reporting things like marginal means and variances from this posterior. And so, we could say that there's a set of nice distributions where it's easy to report things like marginal means and variances. And, it has various distributions within it. We can call them Q. And unfortunately, our exact posterior is not one of those nice distributions. If it were, we'd be done. But it's not. And so one idea for approximating the exact posterior is to say, hey, let's look at all these nice distributions. Let's see how far each one is from our exact posterior, and let's choose the least far one as an approximation. Let's call that Q star. Okay, so more particularly, people often say that they're doing variational Bayes when they're choosing Q star to minimize over the set of nice distributions the Kullback-Leibler divergence in a particular direction between Q and the exact posterior. And the reason I've been sort of using the word far instead of just saying distance and closeness is because the Kullback-Leibler divergence is not symmetric. And so it's not technically a distance, it's a divergence. Now, ADVI, automatic differentiation variational inference, takes this a little step further and says, hey, let's make this a well-defined optimization problem by choosing the nice distributions. Certainly, a set of nice distributions is Gaussians. We said nice distributions are where we can report means and variances. We could easily report that from the mean and variance hyperparameters, variational parameters of the Gaussian. Now, there are two types of ADVI. One is mean field, where sigma is constrained to be diagonal, and the other one is full rank, where sigma can be any well-defined covariance matrix. And we're going to talk about both of those later on. Okay, once we've made the choice for our nice distributions to be these Gaussians, we can transform our optimization problem into the following problem. So in particular, the optimal Q star is completely defined by its mean and variance variational parameters, mu star and sigma star, because those define any Q. Minimizing over the nice distributions is completely equivalent to minimizing over mu and sigma, the variational parameters that define the nice distributions. Now, the rest of this is a transformed optimization objective. So this is the optimization objective that we get out by using this particular variational family. You'll notice there are some functions, g and h. Those actually have very particular forms. For our purposes here, I'm just going to talk about their high-level properties rather than actually defining them explicitly. In particular, first, the thing we want to do with this optimization objective is we want to optimize over it. And the thing to know about G is that it's going to be easy to optimize over. We have analytic access to G. We have analytic access to its gradient. We can do all the usual optimization things with it, no problem. The second term, this integral, it's a little trickier. H is just fine, but we've got to integrate over this normal distribution. Now, of the things we can integrate over, it's about as nice as it can get. It's just a bunch of IID standard normals, but we still don't have analytic access to this integral. We've got to apply at least some amount of approximation, and so we got to think about how to do that. Now, there are two very standard ways to approach optimizing over an integral like this from the optimization literature. The first one, probably most familiar to people, is stochastic gradient descent, or SGD. And if we apply SGD to this problem, we get back the original ADVI algorithm. And so at a very high level, let's just say what this looks like. We decide in advance that we'd like to do something like gradient descent. And so we're going to take a step in the direction of the gradient at any step in our algorithm. And we could consider, and gradient effectively with respect to the variational parameters. And so we consider, okay, we'd like to take a step in the direction of the gradient. That gradient is still an integral over these IID normals. Well, we can approximate that gradient with Monte Carlo. So that's one approach we could take to trying to optimize over this integral. Another one is the so-called sample average approximation. So the sample average approximation just applies the approximation at a slightly different point. In particular, rather than deciding to do gradient descent, looking at the gradient, seeing that we need to approximate it, we instead step back and say, hey, this optimization objective is actually something we could have approximated with Monte Carlo. We could just make our Monte Carlo draws for these normals, and now we have an approximate objective. Conditional on those Monte Carlo draws. Once we have those Monte Carlo draws, condition on them, we are left with a deterministic objective. And we can apply all kinds of standard, out-of-the-box, absolutely up-to-the-minute, amazing optimization algorithms to optimize this approximate objective. These are so similar, and yet we're going to see that there can actually be some pretty substantive differences when we apply them to this problem. And so next, I'm going to talk at a high level about what those differences look like, and then we're going to see a bunch of experiments. I'll just mention that while stochastic gradient descent applied to this problem gets back the original ADVI, the sample average approximation applied to this problem gets back what we're calling deterministic ADVI, or DADVI. Just to be super clear, that is our proposal in our paper. As I said, this is concurrent work with Brony et al. 2024. Both groups published in 2024. We both put our work on the archive in 2023. And actually, both groups have been using this idea in publications all the way back to 2018. Such a great idea, and we've both been enjoying it. But we didn't systematically compare it to ADVI or do sort of a careful evaluation until these latest sets of work. Okay, so what are the pros and cons of ADVI and our new proposal, deterministic ADVI or DADVI? Well, first, let me say some high-level things about both of the methods. They both do this really important thing that we talked about, which is avoiding these manual derivations of update steps. We don't want any practitioners to have to sit down and derive their posterior approximation algorithm. We want them to focus on their important science, social science, and engineering, and leave the algorithmic stuff to the black box Bayesian inference algorithm. On the other hand, there are downsides to both methods. So much like Hamiltonian Monte Carlo, and basically a lot of black box MCMC methods that are being used, these methods require all the parameters to be continuous. And so that does leave out some important models that have discrete parameters. Okay, what about the specific challenges of ADVI? Well, as we said, in ADVI, we're effectively thinking about taking a series of steps in the gradient direction. And so we have to choose a step size schedule for that. And so even though there are ways that are commonly accepted that have theoretical guarantees for choosing step size schedules, those typically involve still tuning algorithmic parameters. And so we either have the situation where we can just use some kind of default and get bad performance in certain cases, or we have to spend a lot of time tuning, which doesn't live up to the black box idea. Two, there's no clear convergence criterion. So traditionally, this was meant to be a big benefit of variational Bayes. When you do Markov chain Monte Carlo, you have this issue of sort of like, okay, I don't really know when it's done. But with variational Bayes, traditionally, you'd have this situation where, okay, I'm changing my parameters. Maybe I could look at something like, gradient norm in the parameter space, or at least that, my changes are effectively going to zero changes. But that's for traditional variational Bayes without this extra Monte Carlo noise. So now we have, with ADVI, this additional Monte Carlo noise in the steps. And so we don't have such a clear convergence criterion as we did anymore. And there's been super cool work, and I'll mention this later, to try to deal with this and come up with a clear convergence criterion. And we'll compare to that as well. Another issue we said earlier is that ADVI inherits this issue of misestimating posterior variances. So this can be true of both mean field and full rank ADVI. We're actually going to see that explicitly later on in experiments. Now, there's this work that we've done in the past that points out that you can do a linear response correction to the covariances to get better posterior covariance estimates. But that work relies on, one, having access to the objective analytically, which we don't have with ADVI, the value of the objective. And then two, it relies on an implicit function theorem. So you effectively have to be, sort of arbitrarily close to an exact optimum of the objective. And we don't have that with ADVI as well. But we're not able to apply these linear response methods, at least without additional work. Okay, and so DADVI basically addresses these concerns. So one, because once we've taken those Monte Carlo draws, we have this deterministic optimization objective that we have full access to, we can use modern off-the-shelf optimization tools. And so in our experiments in particular, we use truss region Newton conjugate gradient. And so again, this is just an off-the-shelf tool in SciPy. Two, because again, we have this deterministic objective. Once we condition on the Monte Carlo draws, we can apply second order methods. So we don't even have to deal with tuning parameters. Three, we're back to having a clear convergence criterion. Again, conditional on these Monte Carlo draws, we have a deterministic objective. And so we can ask, is the gradient norm effectively near zero? Four, because we have now, again, conditional on the Monte Carlo draws, access to our objective, we can actually, evaluate it. This is no problem. And we can get arbitrarily close to the optimum of the approximate objective. We can apply the linear response corrections. And it turns out there's a lot of stuff that basically has a very similar flavor to the linear response corrections, that relies on having access to the objective and applying an implicit function theorem. And so we get more functionality from being able to do that stuff. And so an example of this is estimating what is the variability due to even having Monte Carlo draws. And so we'll see that later on as well. Okay, so now let's dive into a bunch of experiments. So in our experiments, we're going to run on 57 different models. That's 53 applied regression modeling models. These come from a textbook by Gelman and Hill. And then 4 bigger problems, basically more complex and more high dimensional. So these are models in microcredit ecology, elections, and tennis. The parameter dimensions in all of these models range from 2 to 15,000. So we're getting into pretty high dimensional models. Now we're going to run Markov-Chain Monte Carlo as a form of ground truth for accuracy. Now it's worth noting that while we can get up to times about 6 hours of running time for Markov-Chain Monte Carlo, arguably it's much, much longer running times where people really, really want to run variational Bayes. And so there is some bias here in what we're looking at. We're not looking at these gigantic algorithms or these gigantic models where you can't even run MCMC, but hopefully it's still illustrative of what we're doing even in these smaller models. Okay, what we're going to see on this slide is that DADVI converges faster. And of course, computational speed means nothing without accuracy. So in the next slide, we're going to see that DADVI is at least as accurate. Quick note, what does it mean to converge faster? Well, to the user, at the end of the day, what running time really means is how long did it take for their algorithm, for their method, for the thing they're running to finish. The user doesn't want to have to come up with a finishing criterion. They want to run to a default convergence criterion and be done. And so what we're going to do is we're going to take every algorithm's default convergence criterion, or a max of 100,000 iterations, but that together forms a default convergence criterion, and we'll ask how long it takes to run. Okay, so first we're going to look at these applied regression modeling models. And let me just walk you through what we're seeing in this plot here. So we're going to compare to each method in turn, again, on reaching the default convergence criterion. So the first thing we're going to do is we're going to compare it to MCMC, because if MCMC were faster, I mean, we're using it as ground truth. We clearly, trust it in terms of accuracy. So if it were faster, we'd be done. We wouldn't really have too much to do. So we're going to compare it to PyMC's no U-turn sampler for MCMC. On the horizontal axis here, you see the running time of the alternative method, in this case MCMC, divided by our method's running time. And I just want to be really clear, our method's running time includes both sort of base DADVI as well as this uncertainty correction, this linear response correction that I talked about. So both of those are included in the running time. Okay, so in this case, we have this vertical line at 1, and we're making a histogram over all the different models, in this case, these applied regression models. And so if things in the histogram are to the right of 1, our method is faster. If things are to the left of 1, the other method is faster. And so here we're seeing that basically across all these models, our method is at least an order of magnitude faster, sometimes quite a bit more. Next, we look at mean field ADVI, again in PyMC. We're doing the same running time comparison of the histogram over the same models. Not unexpectedly, mean field ADVI seems to be substantially faster than MCMC, but also substantially slower than our method. There's this super cool paper by Well and Dowie et al. That went on the archive in 2022 and has since been published in JAMLR. I mentioned it briefly earlier as having this really cool engagement with this idea that we don't really have a clear convergence criterion for ADVI. So this paper provides a clear convergence criterion. That's a super useful thing to have done. We do find, though, that it is still slower than our method. And then finally, we look at full rank ADVI. Again, not unexpectedly, it is slower than mean field ADVI. That's what we would expect. And so it is slower than our method because, in turn, mean field ADVI is slower than our method. Okay, so these are the applied regression modeling models. What about the bigger problems? So what we're seeing here is these 4 different panels. Each panel now corresponds to a different method. So we have MCMC, mean field ADVI, Well and Dowie et al., and full rank ADVI, just like before. Within a panel, we have 4 bars, one for each of the 4 bigger models, microcredit ecology, elections, and tennis. What was previously the horizontal axis is now the vertical axis. You'll notice both are on a logarithmic scale, so that's still the same. So looking at running time over our method's running time. Now, if things are above, if bars are above the 1 line, our method is faster. If bars are below, the other method is faster. And indeed, we see that for mean field ADVI on the ecology model, the other method is faster, but in general, our method is substantially faster across all of these different models. Now you'll see there's these three X's over in the case of full rank ADVI. Those are cases where we ran our entire compute budget and it still had not finished. Note that that implies that it is slower than MCMC in this case. Okay, so as we said, we notice on this slide that DADVI is converging faster than the alternatives. And so now, and in particular, reaching its default convergence criterion faster than the alternatives. And so now we want to ask, okay, well, that's only meaningful if it's at least as accurate. So is it at least as accurate? And so there's two things that we want to check here. We want to check performance on estimating posterior means, and we want to check performance on estimating posterior variances. We find in our experiments that we're basically the same on posterior means. There's no big difference, and that makes sense because we don't really expect a mechanism for that. But we do expect a difference in posterior variances, and so we're going to look at that now. And I'll encourage you to check out the paper for the comparison on posterior means. Okay, so remember, with DADVI, we can apply this linear response correction for the posterior variances. So we expect these better variance estimates. Let's see if that's actually true. So in this case, we're going to compare it to just the three ADVI methods. So in particular, we're using Markov-Chain Monte Carlo now as our ground truth. So we know if we're getting accurate posterior means or variances. So for each of the different methods, in this case, mean field ADVI, we're going to have a plot like this. Let's talk through what's going on in this plot. First of all, note that there's a point for every parameter. So remember, there's 53 different applied regression modeling models. Each of them has multiple parameters. Some of those parameters could be vectors, in which case we summarize them with a point. We have a point for each parameter. On the horizontal axis, we have our method's relative error for estimating the posterior standard deviation. What do I mean by relative error? I mean, our method returns an estimate of the posterior standard deviation. We compare that to the ground truth posterior standard deviation, which we're getting from MCMC, and then we put that in units, ground truth posterior standard deviation. And so in particular, if anything's above 1, that's pretty bad. And we'd like it to be as low as possible. And again, notice the logarithmic scale in each case. Okay. So now on the horizontal axis, there's our method's relative error. On the vertical axis, we'll have the other method's relative error. So in this case, mean field ADVI's relative error. Now, what are we looking at here? Well, this line, this diagonal line you're seeing, that's an x equals y line. And so if a point's above the diagonal line, our method, that is to say DADVI plus this linear response correction, which remember we also included in the speed comparison earlier, that's performing better. And if things are below the diagonal line, the other method is performing better. And so while we see there are some examples where the other method performs better, by far most of the mass of these points is above the diagonal line. And so we've actually added these contours because a lot of the points sort of bunch up on top of each other. So the contours tell you where most of the points are. Okay, so that's mean field ADVI. We also see, well, in Dowie et al., that most of the points are above the diagonal line. Full rank ADVI, in general, we expect this to perform better than mean field ADVI. And in fact, that's what we're seeing here, that indeed the estimates of the posterior variance are better. But our method provides yet better estimates of the posterior variance. And so we're getting a situation where our method is substantially faster and substantially more accurate. We see this also in the bigger models. So here we have a very similar setup to the ARM models. So in particular, that line, that diagonal line is again an x equals y line. So you'll notice that the axes are slightly different now horizontally and vertically. We still have a point for every parameter or summary over parameter vector. Each point has a shape, and that shape corresponds to the model. So there are 4 different shapes for the 4 different bigger models. And again, we're seeing most of the points are above the y equals x line. We see a similar thing for the Well and Dowie et al. Case. Remember for full rank ADVI that we're not able to run 3 of the models. And so for the one we can run, we see pretty comparable performance between full rank ADVI and our method. But again, this cost can really be prohibitive in these big models. Okay, so again, the big thing that we're seeing here is that we're getting, in general, superior performance in terms of quality, as well as having faster, reaching this convergence criterion And this additional automation can be thought of either as improving quality or just making it so you don't have to worry about, this tuning and things like that. Okay. Now I said earlier that it's not just that we get this better speed and black box aspect and accuracy, we actually get additional functionality. And so now we're going to see what that means in terms of sampling variability. And so I'd like to motivate this with an example. So one of the real life examples that we talked about in terms of bigger models was this microcredit example. So remember, microcredit represents these small loans to individuals in impoverished areas, and the hope is that it's going to help bring people out of poverty. And so economists would like to check, is that true? And so they might look at something like a complex Bayesian model. Indeed, again, we look at a microcredit model in this work, building on existing work from, existing modeling that people have done. And so in that model, it could be the case that there is a particular parameter that describes how much microcredit is helping in a particular way, like increasing small business profit. And so this particular parameter, let's call it the microcredit effect. If it's positive, microcredit's helping. If it's negative, microcredit's hurting. And we're interested in something like, what's the size? How much is it helping? And in particular, we might conclude that microcredit is helping if the posterior mean of this parameter is over 2 standard deviations above 0. That is to say that the posterior mean is positive. Our best guess is that the parameter is positive, and that it's 2 standard deviations above 0. That is to say we believe that with high probability under the posterior that it's positive. Okay, so that's the kind of way we might reach a conclusion using Bayesian inference in this example. But if we used either ADVI or DADVI to approximate our posterior and then try to reach this conclusion, we used Monte Carlo samples to get there. And so we might be concerned, hey, that's some randomness. Could it be the case that the randomness, maybe we got lucky or unlucky, depending on how you're thinking about it. Could it be that that randomness is what actually gave us the result that we got, and it wasn't really merited, like it wasn't a good approximation because it just depended on this randomness. So another way to phrase this is we want to check if we're robust to these choices of Monte Carlo samples. Another way to think about this is, did we take enough Monte Carlo samples? We're essentially asking, did we take enough? And if we're not, if the conclusion is not robust to sampling variability, this is a very practical sort of next step to take, is to just take more samples, take more Monte Carlo samples, which are very easy to take. Okay, so this is a perfect problem for frequentist sampling variability. I mean, these are literally just Monte Carlo samples, all ID from the same distribution. This is, exactly what frequentist sampling variability was made to talk about. So we can look at the frequentist sampling variance of posterior expectations. This is one of these many things that relies on having access to the objective and using the implicit function theorem around an optimum of the objective. And so that's straightforward to do with DADVI, but not with ADVI. We test these estimates of sampling variability in our experiments. And so let me be clear what I mean by testing. So in real life, an actual practitioner is going to run DADVI once. And they're going to, as part of that, we just said, get this estimate of sampling variability. How much would my DADVI conclusion change if I had taken different Monte Carlo samples? So that's an estimate of how much it would change. What we're going to do in our experiments, just for this paper, you would never do this in real life, is we're going to run DADVI many times with many different samples, and we're just going to check, was this estimate of sampling variability accurately reflecting what happened with the actual samples? And we find that it does for a reasonable number of draws. And so the sort of, I think, folklore around Monte Carlo is usually you should take at least 30 draws for just your estimates, much less your estimates of sampling variability. And so it's not surprising that we find that these estimates of sampling variability are not great for 8 or 16 draws. Pretty awesomely, though, for all but one of the data analyses we look at, the estimates are great for just 32 draws. That's not that many draws. That's just 32 Monte Carlo samples. And we find that for all the data analyses, the estimates of sampling variability are great for 64 Monte Carlo samples. And, we really do use this in practice. So we saw those accuracy experiments before where we were getting really good accuracy with our method. In both the speed and accuracy experiments, we used just 30 draws, just 30 Monte Carlo draws. Okay, so let's wrap things up. Today, we talked about how ADVI stochastically optimizes an exact variational objective. And our proposal, DADVI, instead deterministically optimizes an approximate objective, just a slight tweak, really building on some awesome ideas in ADVI, but we get all these new benefits with DADVI. So our paper appeared in JMLR in 2024. There's this super cool concurrent work that I encourage you to check out as well that appeared in UAI in 2024. Both sets of work discuss and describe how we get more reliable optimization by taking the sample average approximation instead of SGD for this particular problem, that we avoid these annoying tuning parameters, and we get clear convergence criteria. Some ideas that are specific to our paper are this idea that we can, because of the setup of DADVI, we can get these posterior covariance corrections, these more accurate posterior covariances, that we get this additional functionality, like these estimates of sampling variability. Something we also show in our paper is that traditionally, in a very general set of optimization problems, you would expect for the sample average approximation to require more samples more compute than SGD, and a large number of samples, a number of samples that grows in a possibly prohibitive way with the number of data points. And we show that in the special structure of many popular Bayesian models, that actually we only need a very small number of samples. And so, a reason that people might have traditionally shied away from something like the sample average approximation is this worst case behavior. But in Bayesian inference problems, we often have this structure that lends itself to a very small number of samples. And so we show this theoretically. So I encourage you to check out the paper for the theory, and also cases where you would not want to use DADVI. And then finally, again, we have this additional functionality. Another thing that relies on, again, this sort of implicit function theorem is sensitivity analysis. So sensitivity to things like the choice of the prior, the choice of the likelihood, to dropping data points. All of these things are types of sensitivity that we've explored in other papers and that are made possible if we were to use DADVI for variational inference. Thank you so much. Really appreciate you tuning into this.